A function f from a set A, the domain, to a set B, the codomain, is a rule that assigns every element in exactly one element f of A and B. Injective or one-to-one means that different inputs never share the same output, formally. For all x sub 1, x sub 2 in A, if f of x sub 1 equals f of x sub 2, then x sub 1 equals x sub 2. Think of a locker system where each key opens a unique locker. If two keys open the same locker, the system would not be injective. Surjective or onto means every element of B is hit by at least one element of A formally. For all y in B, there exists x in a such that f of x equals y. A real-world analogy is a delivery service that manages to deliver a package to every address in the city. No address is left out. A bijection is a function that is both injective and surjective. It pairs each element of A with exactly one element of B and vice versa. Like a perfect dance partner matching where no dancer stands idle and no partner is shared. Explanation: to check whether a given function is injective or surjective, we often turn the definitions into algebraic tests. One-to-one injective test: assume f of x1 equals f of x2 and try to prove x1 equals x2. If you can manipulate the equation and reach that conclusion, the function is injective. For example, for f of x equals 3x plus 5, start with 3x1 plus 5 equals 3x2 plus 5. Subtract 5, divide by 3, and get x1 equals x2. Onto surjective test: start with an arbitrary element y in the codomain, and solve the equation y equals f of x for x. If you can always find a solution x that lies in the domain, the function is onto. For f of x equals x squared from real numbers to real numbers, the equation y equals x squared has a real solution only when y greater than or equal to 0. So the function is not onto real numbers, it is onto 0 to infinity. Both tests can be done directly, or by using the contrapositive colon to show non-injectivity, find two distinct x1, x2 with the same image. To show non-surjectivity, exhibit a y in B that is never attained. Finite set examples. Injective but not surjective. F maps the set 1, 2, 3 to the set of B, C, D, defined by f of 1 equals a, f of 2 equals B, f of 3 equals C. No two inputs share an output, but D is never used, so not onto. Surjective but not injective. G maps the set 1, 2, 3, 4 to the set xy, with g of 1 equals x, g of 2 equals x, g of 3 equals y, g of 4 equals y. Every element of the codomain appears, but many inputs map to the same output. Bijection: H maps the set 1, 2, 3 to the set of B, C, with h of 1 equals a, h of 2 equals b, h of 3 equals c. Perfect pairing. Infinite set examples. Injective not surjective. F maps the natural numbers to the natural numbers defined by f of n equals n plus 1. Every natural number has a unique image, but 0 or 1 depending on indexing is never hit. Surjective not injective. G maps the integers to the integers defined by g of n equals the floor of n divided by 2. Every integer appears as an output, but many inputs, for example 2k and 2k plus 1, map to the same integer, so not injective. Bijection: H maps the integers to the integers, defined by h of n equals negative, and this flips the number line. Each integer has a unique partner and every integer is covered. Counterexamples help solidify intuition. For instance, the squaring function f maps the real numbers to the real numbers, defined by f of x equals x squared. It fails to be injective because f of 2 equals f of negative 2. It also fails to be surjective because negative numbers are never squared to a negative result. Explanation: the type of a function tells us something about the sizes, cardinalities of its domain and codomain. Pigeonhole principle: if a cardinality greater than b, more pigeons than holes, then no function f from A to B can be injective. At least two elements of A must share a hole in B. This explains why a function from a set of 5 students to 4 lockers cannot be one-to-one. Surjection and size. If a cardinality is less than B cardinality, a function cannot be surjective because there are not enough elements in it to cover every element of B. Cantor-Schroeder-Bernstein theorem. If there exists an injection from A to B and an injection from B to A, then there exists a bijection between A and B, meaning a cardinality equals B cardinality. This theorem is often used to show that the set of rational numbers q has the same cardinality as n, even though q seems larger. These ideas help us reason about infinite sets. A function n to n given by f of n equals 2n is injective, n cardinality less than or equal to n cardinality but not surjective. Yet another injection g of n equals floor of n divided by 2 shows that n and the even numbers have the same size, confirming the intuition from Cantor, Schroeder, Bernstein. When you compose two functions, the resulting function inherits properties in predictable ways. Let f from a to b and g from b to c. Injectivity: if g composed with f is injective, then f must be injective because distinct a 1 and a 2 in a would give distinct g of f of a 1 and g of f of a 2. However, g does not need to be injective. A non-injective g can be masked by an injective f if the problematic outputs of g never appear. Surjectivity: if g composed with f is surjective, then g must be surjective. Every c in C must be hit by some g of b, and b comes from some f of a. F itself need not be surjective. Bijection: the composition of two bijections is again a bijection because both injectivity and surjectivity are preserved. This mirrors real life. Chaining two perfect one-to-one correspondences, like two perfect translation dictionaries, yields another perfect translation. Understanding these rules helps when building complex functions from simpler pieces. A bijection f from a to b always has an inverse function f inverse from b to a that undoes f to construct f inverse. Swap the roles of inputs and outputs. For each b and b, find the unique a in a such that f of a equals b, then define f inverse of b equals a. Verification steps. Show f is injective, so each b has at most one preimage. Show f is surjective, so each b has at least one preimage. Define the candidate inverse using the explicit formula or a case-by-case rule. Prove the two compositions are identity maps. F inverse composed with f equals identity a for all in a, f inverse of f of a equals a, and f composed with f inverse equals identity b for all b in b, f of f inverse of b equals b. Example: f from the real numbers to the real numbers, f of x equals 3x plus 4. Solve y equals 3x plus 4. Therefore, x equals open parenthesis y minus 4 close parenthesis divided by 3. So f inverse of y equals open parenthesis y minus 4 close parenthesis divided by 3. Check, f inverse of f of x equals open parenthesis 3x plus 4 minus 4 close parenthesis divided by 3 equals x. And f of f inverse of y equals 3 open parenthesis y minus 4 close parenthesis divided by 3 close parenthesis plus 4 equals y. The inverse exists because f is a bijection, linear with non-zero slope. Mathematicians use several proof styles to establish injectivity or surjectivity. Direct proof: start with the definition and manipulate it straight to the conclusion. For injectivity, assume f of x sub 1 equals f of x sub 2 and algebraically derive x sub 1 equals x sub 2. For surjectivity, take an arbitrary y in the codomain and explicitly solve for x. Proof by contrapositive. Instead of proving if a then b, prove if not b then not a. For injectivity, the contrapositive is: if x sub 1 not equal to x sub 2, then f of x sub 1 not equal to f of x sub 2. Showing distinct inputs give distinct outputs can be easier in some contexts. Proof by contradiction. Assume the opposite of what you want. For example, assume the function is not injective and derive a logical impossibility. This is handy when a direct algebraic root is messy. Choosing the right style depends on the function's form. Linear functions usually lend themselves to direct proofs, while piecewise or combinatorial functions may be clearer with contrapositive arguments. Explanation: typical exam tasks include: classification. Given a table or rule, decide if the function is injective, surjective, both, or neither. Example: f of 1 equals a, f of 2 equals b, f of 3 equals b, f of 4 equals c. Students identify that f is surjective, covering all letters but not injective because 2 and 3 share b. Proving a bijection. Show that the function f from natural numbers to natural numbers defined by f of n equals 2n is a bijection between the natural numbers and the even numbers. Students must prove injectivity. 2n sub 1 equals 2n sub 2 implies n sub 1 equals n sub 2, and surjectivity onto the even set. For any even m there exists k such that m equals 2k. Finding inverses. Given f of x equals x minus 1 over x plus 2 on a suitable domain, solve for x in terms of y to write f inverse of y. Counting via bijections. Demonstrate that the number of ways to choose a committee of k people from n is equal to the number of ways to choose n minus k people to exclude, by constructing a bijection between the two selection sets. This shows n choose k equals n choose n minus k. These questions test understanding of definitions, ability to manipulate algebraic expressions, and skill in constructing explicit one-to-one correspondences. Injective one-to-ones. Necessary condition. No two different elements of the domain map to the same codomain element. Test, assume f of a equals f of b, implies prove a equals b. Pitfalls, forgetting to consider all possible cases, for example piecewise definitions. Ignoring domain restrictions that could cause collisions. Surjective onto. Necessary condition. Every element of the codomain is hit by the function. Test, take arbitrary y in the codomain, solve y equals f of x, implies show a solution x exists in the domain. Pitfalls, assuming range equals codomain without checking, overlooking values that have no preimage, like negative numbers for a squaring function. Bijective. Must satisfy both checks above. Inverse existence. After proving bijection, write down f inverse and verify f inverse composed with f equals identity and f composed with f inverse equals identity. Pitfalls, forgetting to verify both directions of the inverse, or using a formula that only works on part of the codomain. General tips. Always write down the exact domain and codomain. Changing them can flip injectivity or surjectivity. Use counterexamples to test hypotheses. Find two distinct inputs with same output, which breaks injectivity, or a codomain element with no preimage, which breaks surjectivity. For composition questions, remember, injectivity of the composite forces the first map to be injective. Surjectivity forces the second map to be surjective. When constructing an inverse, start by swapping variables and solving, then double-check with composition identities.